Well, I see we have at least 3 of the first 4 speakers here and some others, so that's good. We need to get started right on time because I'm told by the organizers we will be shut off. Oh, hi, Joshua. Glad you made it. We will be, and Michael, good, you're here. We'll be shut off 15 minutes after our end time, which would make it 1:05. So we have to stay pretty close in time. Couple announcements. If you have a question, use the reactions button right next to the end button in Zoom, and it gives you an option to raise your hand. Let's see, the talks will be 17 minutes with 3 minutes of discussion, give or take. And anyone who would like more discussion can, we can set up the breakout room. It's already an option there. And during the talks, please mute your mic and your video. And let's see, we're about getting ready. So I'll ask Kotaro Tanikawa to set up his start sharing slides. And in 1 minute, we'll start up.
Okay, let me start my talk. Can I start?
Please.
Okay. Okay, hello everyone. I'm Ataru Tanikawa from the University of Tokyo. Thank you for giving me a chance to talk here. And thank you, Mashu, for adjusting me for Japanese time zone. So today, I'd like to talk about the importance of convective overshoot for the formation of mass gap event GW900521. And they are my collaborators of this study. Okay, let me start my talk. Okay, as you know, GW190521 has been reported last year with a big surprise. This is a merger of 85 solar mass and 66 solar mass black holes. At least the heavier black hole mass can be in the so-called pair instability mass gap. And there should be no black hole in the mass gap range. So many scenarios have been suggested to form GW190521. And let me categorize the scenarios in this session. So please correct me if I misunderstand anything. So there can be uncertainties of the mass estimate in the data analysis. So the heavier black hole can be beyond the mass gap and the lighter black hole under the mass gap. So in other words, this event can have 2 black holes straddling the mass gap. So if this is true, the event is no problem. So because the black hole is not in the pair instability mass gap. And there can be uncertainties of the mass gap boundary because of microphysics in stellar evolution, such as the carbon alpha gamma reaction rate, screening effects, and dark matter effects. If this is true, the mass gap range shift to possibly upper side. So yeah, this this mass itself is not in the pair instability mass gap. And today, I'd like to let you know that macrophysics in stellar evolution, in particular, convective overshoot, also play an important role on the formation of the mass gap event. And this is the basic idea to fill the mass gap. Please note that we assume the standard microphysics in stellar evolution. So for example, the carbon alpha gamma reaction rate is sort of the standard value I adopted. So in single star evolution, a mass gap black hole can be formed relatively easily. Let's consider a massive metal poor star. Because of its low metallicity, it experiences weak stellar wind mass loss. So it doesn't lose mass until its pre-supernova phase. It doesn't experience pair instability because its helium core is small. Finally, it leaves behind a mass gap black hole. In this case, the mass is 90 solar mass. The formation mechanism of mass gap black holes has been previously suggested by population synthesis calculations and stellar evolution simulations. The point to form a mass gap black hole in single star evolution is the presence of massive hydrogen envelope. But the formation of a mass gap BH is black hole is not easy in binary star evolution. Let's consider massive binary stars. The binary star should be very close because it should merge within the Hubble time. And even if the star doesn't lose mass through stellar winds, it loses most of its hydrogen envelope through binary interaction. Then it becomes naked helium stars and leaves behind a black hole below the pair instability mass gap. But if the star keeps its radius small until its supernova, it can avoid losing its hydrogen envelope through binary interaction. Finally, it can form a mass gap black hole. So the point in binary star evolution is if a star can keep its radius small or not. But metal-rich stars observed in the local universe cannot satisfy the two necessary conditions to form mass gap black holes. The solar metal stars or POP1 stars lose their hydrogen envelopes largely through their stellar winds. And the POP2 stars, relatively metal-poor stars, lose little mass through their stellar winds, but expand to more than 1,000 solar radii. So the star should lose its hydrogen envelope mostly through binary interaction. So POP1 and 2 stars are difficult to form mass gap black holes in binary star evolution. And so before proceeding further, I'd like to introduce the key process, convective overshoot. This is the main process in this talk. The convective overshoot is a mixing process around the boundary between convective and stratified regions. We can see the convective overshoot on, for example, thundercloud top here on the Earth. Here is a troposphere, and this is a stratosphere. We can see a cloud invades into the stratosphere. This is because of the convective overshoot process. And the convective overshoot can happen inside a massive star. A massive star consists of a convective core and radiative stratified envelope. The convective overshoot happens at the boundary and mixes material in the two regions. In the two regions means a convective core and radiative envelope. And the convective overshoot strongly affects POP3 star evolution. Here, POP3 stars mean metal-free stars or fast stars. They don't lose mass through weak stellar wind because of zero metallicity. Moreover, POP3 stars can keep their radii less than 100 solar radii if convective overshoot is not efficient. Please note that they expand to more than 1,000 solar radii if convective overshoot is very efficient. The reason why POP3 stars largely depend on the convective overshoot is as follows. This is the structure of a massive star. Again, it consists of a convective core and a radiative envelope. And convective overshoot can transport materials in the radiative envelope to the convective core or the stellar center. So if convective overshoot is less efficient, a smaller amount of hydrogen is burned, and a smaller helium core emerges at the end of the main sequence phase. Such a smaller helium core emits a smaller luminosity, and such a smaller luminosity less expand the star. And actually, POP1 and POP2 stellar radii are not sensitive to the luminosity difference because POP1 and 2 stellar envelopes have large opacity because of the high metallicity. So the both luminosity can expand the star largely. But the POP3 stellar radii are very sensitive to the luminosity difference because POP3 stellar envelopes have small opacity because of the zero metallicity. So the luminosity is very important for the POP3 stellar envelope, POP3 star radii. And so we perform population thickness calculations adopting the POP3 model with a less efficient convective overshoot. Additionally, as a reference, we also use the POP3 model with a more efficient convective overshoot. And this is the overview, a brief overview of my calculations. This is Zam's and final mass relationship for POP3 single star evolution. So mass gap black hole can be formed because of zero metallicity and because of single star evolution. And this is a regime of pulsational pair instability, and this is a regime of pair instability supernova. So there's no stellar remnant. And we adopt conservative POP3 formation rate like that, and we adopt a sort of top-heavy IMF for POP3 stellar IMF. Such a top-heavy IMF is obtained from numerical simulations for POP3 star formation. And this is the result. This figure shows the major rate density differentiated by the heavier black hole mass. This is heavier black hole mass, and this is differentiated by the lighter black hole mass. And the redshift is 0.82, which is a redshift of the mass gap event. And these points with error bars indicates the values of GW190521. And in the less efficient overshoot model, the maximum black hole mass is 100 solar masses. And the major rate density is also consistent with the gravitational wave observation. In other words, POP3 stars can form GW190521 if convective overshoot is not efficient. In the more efficient overshoot model, the maximum black hole mass is 50 solar mass. So POP3 stars cannot form GW190521 if overshoot is more efficient. So POP3 stars can form the mass gap event if convective overshoot is not efficient. So this means the convective overshoot plays a very important role on the formation of the mass gap event. And so let me discuss how to assess our POP3 scenario. Even if the less efficient convective model is correct, POP3 stars cannot form black hole mergers with 100 to 130 solar mass. On the other hand, if the other scenarios, such as hierarchical merger scenarios, are correct, there is no mass gap in this range. So yeah, so if such a mass gap cannot found in the by the near future gravitational waves observation, our scenarios can be rejected. And if such a mass gap is found, our model at least survive. Of course, other scenarios can explain such a mass gap. So the discovery of mass gap is not conclusive to confirm our POP3 models. Okay, this is summary of my talk. Yeah, so this is a take-home message. The convective overshoot is very important for filling the mass gap and mass formation of mass gap event like a GW190521. Okay, this is it. Thank you for your attention.
Thank you for that very interesting talk. Let's see, are there any questions? I see a couple of hands have come up. Maya has a question, and Amedo.
Yeah, thank you for the very interesting talk. I was wondering about this, even in the case where you have inefficient convective overshooting, and you have this like second mass gap, then the mass gap only starts at like 100 solar masses. I was wondering how robust that 100 solar masses is, or what are there any uncertainties in determining that, or is that a kind of firm prediction?
So you mean what determines the upper limit of the black hole mass? You mean?
I mean, yeah, like in the comparison, there was a slide comparing the POP3 versus the cluster, and the cluster origin would fill the gap entirely, but in your scenario, there would be this mass gap. So in terms of the boundary of that mass gap.
This mass gap is this is overcome pair instability supernova. And this boundary determined by the helium core mass, because in a model, so the helium core, if helium core mass is more than 45 solar mass, we assume pulsational pair instability occurs. So it depends on the how to say. It depends on the helium core mass. I got the point. Your point, Maya?
Yeah. No, my question was just like, is that 100 solar masses kind of firm, or could it be like between 110 and 130 solar masses that there would be a mass gap?
it is not firm at all. The mass gap may not exist at all if you take reaction rates plus dredge up. And it could be 70 or it could be 80. We simply don't know. It's convenient to pick 90 or 100 because it fits GW 1905-21, and that's what we think nature is telling us via this LIGO observation, that it should be somewhere around 90 or so. I mean, that's my take on it.
Okay, well, Christoph, since your hand was up, was that what you wanted to say? Or did you have
No,
another
no,
question?
no. I had a more physics-related comment to Ataru. Actually, assuming that a helium core mass is below or above 45 solar masses, it's not enough to decide whether a core is unstable to per-instability explosion or not. What is important is central temperature and density, and mass is only a second determinant here, or a third determinant. So actually, by assuming that you have hydrogen envelope plus 40 solar mass core, it means that your central profile of temperature and density are probably over per instability pulsation supernovae in a standard reaction rates regime. So I think you implicitly assuming that reaction rates are lower than standard without realizing.
You mean so? You mean I actually I assume the okay. I actually assume the reaction rate is lower than I assume.
You do.
Okay. So is there any reference for your
yes,
your
I
saying?
will talk with you offline, and probably should have a small chat on Zoom some other day, and I will explain what I mean in detail.
Okay.
Okay. Thank you very much. Thank you for your comments.
Move on to the next talk. But Amado, do you have a quick?
Yes. I just would like to know how you define efficient and not efficient overshooting. I mean, is it a number? Is it something else? What is the clear distinction?
So I mean, so definition of the efficiency of the overshoot. Do you mean?
Yeah, exactly.
So yeah, we use a sort of a free parameter for overshoot, convective overshoot efficiency. So it determines by the in a model the a sort of a mixing length from the mixing height from the convective core embedded with the radiative envelope. Yeah, and the mixing length is difference 3 times. So I mean that if less efficient mixing length is 3 times smaller than the more efficient models.
Okay.
We need to really move on to the next talk now. Maya, can you begin sharing your slide and ask everyone to mute out again? And Maya will give us lessons from LIGO Virgo's biggest black holes.
Yeah, thanks so much for organizing this session, Grant. It's really nice to see an entire session on the black hole mass gap. So I'll be focusing mostly entirely on observations and gravitational wave observations. So I will leave all the theory interpretation to the other talks in this session. But just to get started, so I'll be talking about the detections that LIGO and Virgo have observed in the first 2.5 observing runs. So the latest catalog by the LIGO Virgo collaboration is the second gravitational wave transient catalog, or GWTC2. And with that, there's a catalog paper that contains all of the events that were found with high significance and their parameter estimation. And there's a populations paper and a tests of general relativity paper. And I'll be mostly talking about results from the population paper, as well as some other external to LIGO Virgo papers. So in the catalog, This is the plot that shows the 90% probability contours of the masses of the events. And this is just the new events from the first half of the third observing run. And the total mass and mass ratio. So you can see if we're talking about the biggest black holes, we're talking about the highest total masses. So the most extreme one in this category is GW 190521, which we've already had a great introduction to as part of Ataru's talk. But you can see that there are also these other pretty big black hole binaries. And so I'll be talking not only about this one event, but kind of this whole population. And to do that, we have to do a population analysis. So rather than talking about the parameters of the individual events, like in the last plot, it was the total mass and the mass ratio, which we can measure for each event separately. We can also measure the distributions of these parameters across events. So we want to describe the distributions of the masses, spins, and redshifts across the entire population of gravitational wave events. And so an example that I will start with is fitting a power law with some maximum mass to the black hole primary mass distribution. And to do that, there's some formalism you have to do to take into account the measurement uncertainty and selection effect. So unfortunately, it's not as simple as like staring at the previous plot and trying to draw a line where the maximum mass is. And this is, so here I've just put a bunch of bullet points of all of the astrophysical lessons that we have, at least in this LIGO-Virgo populations paper. And I'm not going to talk about all of them, especially because the session is focused on the black hole mass gap. So I'll just be talking about this first one, which is what is happening with the black hole mass spectrum above 40-ish solar masses or so. So I'll talk about three main things, the where, what, and when of this mass gap. So starting with where, so one thing that I think is important to note is that there is evidence that there's some feature in the black hole mass distribution at 40 solar masses or so. And this was clear just from the first 4 events, where all of those first 4 events had a total mass below 80 solar masses or so, despite the fact that our sensitivity, so the co-moving volume that the gravitational wave instruments are sensitive to black holes, increases pretty steeply as a function of mass. So it was significant that even though these biggest black holes should have been the loudest and the first ones we should have seen, we didn't. And this turned out to be pretty significant and allowed us to conclude that these more massive systems with total masses above 80 solar masses or so are intrinsically rare in the underlying population. And that was true from the first observing run, from the first 2 observing runs, and it remains true even after the 3rd observing run. Even though now we know that there are events that are more massive, there are still relatively few of them compared to how sensitive the gravitational wave observatories are. But going back to just the first 10 binary black holes, back then, the data was consistent with being this simple power law distribution with some sharp maximum mass cutoff. And we measured this maximum mass cutoff to be around 40 solar masses and concluded that this was extremely consistent with predictions for the apparent stability mass gaps, and it was consistent with being a sharp cutoff. So that was all great. In detail, this is the posterior probability distribution that we got for the maximum mass. So just this sharp cutoff in the distribution around 40 solar masses with some uncertainty. And just for comparison, here are the individual primary masses inferred under uninformative parameter estimation priors for the 10 events that went into this measurement. Okay, but then we know that the picture is more complicated with the 30 plus new events from the third observing run, especially with 1905-21. So what about this event? We already heard about it, but I think the fact that there's this whole session speaks to how exciting this event is. And here is GW 1905-21 in the context of that population that I showed. So this blue posterior here is the same maximum mass posterior as the earlier plot that we measured from the first 10 events. And here, the gray shaded bands are just now showing the 90% credible regions for the primary masses of all of those events. In pink is 1707-29, which is the most massive event previously that we had from the first two observing runs. And then in finally in green and in orange is the primary mass here and the secondary mass for 1905-21. And one thing you can see here is that the secondary mass of 1905-21 actually does overlap with the maximum mass measurement from the other 10 events. So if we think that this secondary mass maybe is part of the same population of black holes that we've seen previously, we can put this new prior on the masses of 1905-21, and we get that so in purple here is the primary mass versus secondary mass probability contours under the uninformative prior, so just flat priors on the masses. But if we think that the secondary mass is actually below the maximum mass that we measured before this sharp cutoff, we push the secondary mass to lower masses, so lower masses here. And because this total mass for the system is well constrained, the fact that the secondary mass, we think it is probably lower mass, actually on the low end of its posterior, that pushes the primary mass to be slightly larger and actually increases the support that this primary mass is above the 120 solar masses. And if we consider that this region here between 45 and 120 solar masses is the mass gap, if you assume that the secondary mass of 1905-21 is below the gap, then it actually becomes quite likely that the primary mass is above the gap. And so you have this straddling binary. So that is one interpretation of GW 1905-21 that is kind of interesting. But for the last part of this talk, I will actually assume that the primary mass of GW 1905-21 is between 65 and around 100 solar masses, which is for technical reasons where we cut off our population inference. So I will actually assume that it is closer to what you get in the uninformative prior. It's around 70 solar masses or higher. And the reason for that is because now that we have all of the data from GWTC2, the first half of the third observing run, there are other black holes that are likely above 50 solar masses or so. So now it seems like 1905-21 might be part of this population of big black holes that are perhaps unexpected based on the first two observing runs. And to see that in this plot, you can see the maximum mass that we measured from the first two observing runs, or GWTC1. And here, if we assume that the mass distribution is just some power law with a sharp cutoff, we get that the maximum mass, even without 1905-21, has to shift to higher masses to accommodate these more massive events, which are seen in these black dashed and dotted lines. If we include 1905-21, the maximum mass must increase even more. And our conclusion here is that the mass distribution must just be more complicated. It's not a straight power law with just some sharp cutoff. Otherwise, it shouldn't be so sensitive to putting in and taking out different events. So I will now distinguish between these different mass models we can use to fit the data. Some of them are just this truncated power law. So this here we have a sharp cutoff, just one power law slope with a sharp cutoff. But then we can add more complicated models like a broken power law or a Gaussian peak on top of the power law. So focusing just on the broken power law for now, you can see that here, when we fit the data to this broken power law model, we still find a feature at around 40 solar masses, after which the mass distribution decreases more steeply. So there's kind of some excess of black holes, which you can also see in the power law peak model, up to around 40 solar masses. And then there is some steeper decline, but it's not infinitely steep. So it's not an infinitely sharp cutoff, it's maybe more of a tapered cutoff. So the astrophysical interpretation of this is completely open, right? Are the big black holes above this break, for example, inside the mass gap, and are they made in a different formation channel? Is it just that the mass gap actually starts at 80 solar masses? Whatever we're seeing here has nothing to do with pair instability. It's just some other feature. But something that I'll mention in the last couple of minutes is that it's also possible that the mass distribution is different at high redshifts than at low redshifts. So I'll just take like 1 or 2 minutes to focus on this last part, which are this when. So you can get an idea of this from this plot, which shows the primary mass versus the redshift. Again, these are different blobs showing 90% credibility contours for the different events. In blue are the ones we had from the first 2 observing runs, and in orange are the new events from the 3rd observing run. And you can see that in the 3rd observing run, we're now probing out to higher redshifts, and all of these more massive events we've seen we find them at higher redshifts. So there are 2 possible explanations for this. Either these more massive events are just rare overall, and there's just more volume at higher redshifts, so we just found them first, or there really are these missing events here, and the more massive events only occur in the universe at higher redshifts because of something like evolving metallicity or other explanations, which I will not attempt to explain in this talk. Just talking about the data. So again, one possible interpretation is that they don't make them like they used to. There may be some hints that black holes are bigger at higher redshifts earlier in cosmic time than they are today at low redshifts. And this depends a little on whether this depends pretty significantly on whether you assume that the mass distribution has a sharp cutoff or a more tapered cutoff. So the truncated model, sharp cutoff versus the broken power law, where you still have some feature, but the cutoff is not super sharp. And so if we have this more tapered cutoff in the broken power law model, when we allow the mass distribution to evolve, it's still consistent with this 99th percentile of the mass distribution staying pretty flat at between 40 and 60 solar masses across all redshifts. But if we say that the cutoff in the mass distribution has to be sharp, then it must evolve with redshift. And so it could be that there's some sharp cutoff due to pair instability, but it's 40 solar masses at low redshifts and has to increase to 60 solar masses or higher at high redshifts. So this is basically what I just said, and in the interest of time, I will just end on my conclusion slide. So these are the things I talked about: the where, what, and when. I think there's this possibility that the mass distribution evolves with redshift, and I know that there are a lot of theorists here in the session, and so I would also like to possibly have discussions about that, about whether any of these explanations would predict for this mass evolution with redshift. And I'll end here.
Well, thank you, Maya, for a very interesting talk. This paper is open for discussion now. We have some time. Oh, yes, there's one hand up. Christoph?
Hi, Maya. So I would like to change. It was all very interesting about masses. Thank you for giving that overview, especially the fact that it's possible that the mass evolves with redshift. But I wanted to ask about something more controversial. People are kind of claiming in some papers that eccentricity or actually even rotation of those black holes could be high. How is your feeling about that? We know a lot about masses right now. What about those other secondary estimates of those other parameters?
Yeah, so JW 190521 is a very difficult system to analyze, and it's really pushing the limits of what waveform models can do right now. And so and I think especially with just one system, like there are hints that maybe it has significant precession and that maybe it also has eccentricity or one of those. But I think it's very hard to tell because I think with one system, we can never have very conclusive evidence, but also because of the systematic uncertainties that this system is only in band for a few cycles. It's really just like the merger part of the waveform and the ring down, which we have difficulty modeling anyway. And then, so it's very possible that there are just systematic uncertainties in the waveforms. And so when you add a knob like precession or eccentricity, the data favor that because the default model is not a good fit. But the fact that the default model is not a good fit is not so surprising given how difficult it is to model these very massive mergers.
Thank you. That confirms what I thought. Thank you.
Sam has a quick question.
Yeah, great talk. Yeah, so I was also kind of wondering about this question of the multiple posteriors, and there's this new paper by the IS group that kind of explores all the different prior assumptions and stuff. And I know you and I have talked about this before. I was just kind of wondering if you had where your personal hyper posterior was now, or do you feel like it's more likely that it's straddling or?
Yeah, so I think I kind of brushed this aside, but in these later papers, these later population analyses, I've assumed that it's not straddling, mostly just because of this technical limitation in that the way we measure our sensitivity in LIGO, we only did injections up to 100 solar masses because we didn't think that we'd have to worry about this. But yeah, I definitely think that in the future, we need to just fit for the possibility of a population, like do the full population analysis and allow for systems above 100 solar masses. And then the whole question of what prior you use for individual systems becomes not really relevant because you're doing the full population analysis. So yeah, I think it's completely an open question right now, but hopefully we'll know answers soon.
Okay, we need to move on to the next talk. Thank you again, Maya, for a great talk. And we should hear from Mathieu Luciana.
Hi.
Oh, there you are. Good. So please share your slide and begin.
Okay. Can you see it?
Yes.
Excellent. So yeah, thanks for giving me the opportunity for giving this talk. I'm going to explain the last work we performed about parameter estimation for gravitational wave signals in or near the Peristaltic supernova mass gap, more in concrete for GW 190521 and other high mass events. So yeah, just briefly, because in the other talks was also introduced, 190521 is a very high mass event, and the remnant mass is in the intermediate black hole range. And at least the most massive component mass is inside the Peristaltic supernova mass gap. Is a very challenging signal because it's a very short transient, about 0.1 seconds. So the main part of the SNR is due to the ring down. So as you can see here in the plots of the waveform, being the dashed red line, the maximum waveform, we can see that there is a strong suppression of the spiral cycles, and this prone to not resolve degeneracies. So how can we trust our results? How do they depend on the waveforms, the sampler settings, or the prior? So this is the question we are going to try to answer during this talk. Another important thing of this event is that there are also electromagnetic counterparts, an association with AGN flare, which is not clear. And yeah, so now we have like a review of the event that we are going to talk. Now, let me introduce a bit about the importance of waveform models and which is the current status of them. So at the end, for performing the inference of source parameters like masses, spins, and so on, we need such accurate waveform models. And these waveform models are a mixture between numerical relativity and perturbative results. At the moment, there are three main different families of waveform models, which are code-based in the LIGO algorithm library and are reviewed by the LIGO-Virgo collaboration. First of all, we have the surrogate models, which do an interpolation of NR waveforms. But in terms of the parameter space, they are quite limited. Then we have the effective one-body waveform models, which model Hamiltonian and radiative flux, and then solve the ODEs, which are quite computational expensive waveform models. And finally, we have the phenomenological ones, which combine piecewise closed forms expressions and are very fast waveform models. So the waveforms are just sum of spherical harmonics, and once we add the higher mode content, we gain accuracy in our waveform models. So at the moment, in the O3 analysis, it is starting to be used all these waveform models that include these multi-mode spherical harmonics. At the moment, there is not a generic waveform that includes spin precession and eccentricity. For the moment, we only have non-precessing and non-eccentric models calibrated to NR, and the ones with precessing, the calibration to NR is still quite limited. Now we have an overview of the waveform models we have. Now let me tell you about the fourth generation phenomenological waveform models, which were developed by our group. There is a non-processing sector, which is calibrated to NR, and then the processing one, which is based on twisting-out approximation. We can split into two different families, one in the frequency domain and another one in time domain. So the frequency domain, IMR phenom XPHM, is an upgrade of the main used phenomenological wafer models until last years, like IMR phenom D or IMR phenom PV2 and other versions. On the other hand, we have the time domain model, IMR phenom TPHM, which take all the techniques from frequency domain to time domain. And this allows us to improve the treatment of precession. Like, for example, if we are working on time domain, we avoid doing Fourier transforms. So at the end, we are dropping the stationary phase approximation. Apart from these improvements, we also can introduce analytical information about the ring down frequency for the processing waveform. And that's really interesting and important for the analysis of GW 1905-21, because as I said before, the main SNR was due to the ring down. So at the end, we have quite fast phenomenological waveform models in both time and frequency domain. And this allows us to do a lot of systematic studies, like testing sampler settings and doing convergence tests, testing different priors and doing some waveform systematics. Now, let me talk about a bit the previous results about GW 1905-21. So LBC did firstly the analysis on this event, and they used a prior above 0.17 mass ratio. And this mass prior excludes the maximum likelihood regime, and also excludes some other modes in the posterior corresponding to unequal masses. Nitz and Capano, in their paper, analyzed wider priors. In fact, one that gives more support for unequal masses, 1/Q prior with XPHM. And here in these plots, you can see their results. So in the bottom, we are plotting the mass ratio against the chi effective, which is the average spin orthogonal to the orbital plane. As you can see here, they found 3 different modes for very unequal masses, correlated with very negative chi effectives. They found quite multimodalities in the posteriors, as you can see also here when we are plotting the component masses. And in fact, for small q's, they found that the mass sources were outside the peristability supernova mass cap. There are many other studies about this event using different physical interpretations. And for example, adding eccentricity, or as was commented in the previous talk, adding population-informed mass priors. Now, I'm going to talk about what we have done in our work. So, seeing all the different results, all the different previous results, we decided to perform a very deep study on 1905-21, not only using IMR phenom X, but also this improved time domain model IMR phenom T, and also see how results change with different prior choices. Just to be very confident with our results, we decided to do a convergence cross-check, and we performed 2 different types of runs using 2 different sampling codes. Firstly, we use a Markov chain Monte Carlo algorithm implemented in LAL inference, which samples in Q and in chert mass. and always does a reweighting into the prior flattening component masses. On the other hand, we also decided to perform other runs using nested sampling algorithm, which is implemented in parallel within the library dynasty, which also samples in Q and in shape mass. But then afterwards, we have to do some reweighting in order to compare all the results. Here you have the details of the parameter estimation settings we used, but I'm going to skip that. So yeah, now let's be focused on the prior choices we used. One can use astrophysical priors, but if we have some unexpected results, we could miss them. So we decided to use uninformative priors, but be careful, because for example, for the LBC priors, they undersample the small Q regime. So at the end, we decided to use the same prior used in Nitz-Capano paper, the inverse in mass, the uniform in inverse mass ratio, which gives an emphasis to unequal masses, as you can see here. And we run into the detector frame in order to take advantage of some of the parameter estimation settings that we were using. And afterwards, we did a reweighting in order to compare all the results with the same thing. Apart from these prior choices, we also decide to do high resolution runs, just focusing on restricted priors for the mass ratios. And we use, for LAL inference, we use a range between 0.035 up to 0.15, and for parallel BLB runs up to 0.20. Apart from these priors, we also decide to check the electromagnetic counterpart. So we fix the sky location and the distance to the active galactic nuclear flare. However, our results are not robust. So here you have all our plots of our results. Here on the bottom, we are showing a restricted posterior of the mass ratio, where the blue curve is the run that we performed with a wide mass ratio prior, and then the green is the one that was restricted to above up to 0.2, and the orange one up to 0.15. As you can see here in this zoom, we are missing this this mode, which gave support for more extreme mass ratios that was appearing in Nitz-Capano results. Having a deep look into the parameter estimation results, here we can see that for our time domain model, we are recovering a positive chi-effective. However, for a frequency domain model, we are recovering negative chi-effective. If we want to have a look for the precession spins, we can have a look to the quantity Kp, which is an average spin of the precessing orbital frame. And for the time domain model, we are recovering a higher precession spin. Also, we are recovering for these wafer models a higher livelihood. And a point that has to be said is that the maximum livelihood values, which are marked with these stars, which corresponds to these values over here, can be influenced by statistical fluctuation. So they depend on the sampler setting we are using, the prior choice, our prior choices, and also with the wafer models that were used. Now let's talk about the mass gap. So as you know, the boundaries of the gap are very uncertain. So we decided to test two different possible ranges. One, the low one, which is between 50 and 120 solar masses, and a high one, which is between 70, and 160 solar masses. Here we are comparing the previous results by Nitsan-Capano and the LVC and our own results. And as you can see, and I said before, the Nitsan-Capano results had here the more unequal mass peak outside the mass gap. However, in our results, we are at least one of the two component masses for the low boundaries is above 70%, and for the high gap is above 85%, the probability of being at least one inside the gap. But just to clarify a bit more all these results, let me explain you a bit this table where we are showing you the probability that the mass 1 is inside the mass gap, the probability of mass 2, the both are inside the mass gap, or one or the other one are inside. So here, the first part of the table, we are showing the results for the time domain model, which has this new information, this new analytical information about the ring down frequency for the precessing waveforms. So they are solving better the results, in that case for GW190521. And first of all, in that table, we can see that for the non-precessing and the XPHM using the uniforming component masses priors, we are recovering more support for being at least one of the two masses inside the parent stability mass gap. About the time domain model TPHM, the probability is a bit lower than XPHM, but we can see that there is a good agreement between different mode content of the spherical harmonics, and also for different waveform model versions. Finally, using the Nitsan-Capano prior, our probabilities are much smaller. So the probability of both component masses lie inside of the mass gap are much smaller. So finally, just let me talk briefly about another high mass event, which is 170729. It is the most massive and most distant event of the first catalog of LVC. And here you have a table where it's shown that there is mild evidence of higher mode content. Here are shown the bias factors comparing a higher mode waveform model against a 2-2 mode waveform model. So adding higher mode and precession to the waveforms to our PE analysis, we are recovering more unequal masses, especially for TPHM. So this time domain waveform gives us a shift to higher M1. So the more massive component mass is beyond the onset of the low mass gap. And finally, we also decided to cross-check the influence of priors in this event also, in order to avoid missing any extra information about more unequal masses. So we decided to use also the same prior as before, 1/Q, but we are recovering the same results as with the LVC previous priors. So here we are not seeing any other multimodality as before. And yeah, let me just explain the conclusions. So having a high mass and short signal is very challenging for the waveform models and also for the parameter estimation. because prone to multimodalities in our posteriors and also giving us high mass ratios, spins, and eccentricity. The results depends on the prior choices we are using. And in our case, our results for 1905-21 don't have support for intermediate mass ratios. However, we have high spins, but the final spin is not tilted. We are very confident with our results because we have compared different sampler different sampler codes, and they are consistent between each other. And unfortunately, at the moment, there are no generic waveform models which join spin precession and eccentricity, because it would be quite interesting to reanalyze this event with some generic waveform model. But in our case, we are assuming quasi-circular orbits. And about the mass gap hypothesis, our aligned spin models and also XPHM gives support for this hypothesis. And TPHM has also support, but a bit smaller. However, for XPHM using the inverse mass ratio prior, the probabilities are mild. In the future work, we are also planning to do the same deep study for other high mass events in O3. And yeah, that's it.
Thank you, Maddie, for a very interesting talk. Christoph has a question.
Yes, GW 1905-21. What's the best value for a low effective spin? For effective spin parameter, sorry. Is it low or is it high?
Sorry, I'm going to. So you mean for the chi effective?
Yes, chi effective. Just give me a number. What would be your best guess?
So, I don't know. So
you don't know. Okay, I will private answer, but I would like to hear value if you have one.
I don't know now. Well, I can have a look to the tables if you want now, because I have the paper in front of me. That in memory, I don't know. So the thing is that here in this plot, just so we are recovering. So as I said before, for the time domain models, we have these improvements. So at the end, it's more likely to be positive than negative, because XPHM in here has some approximation. So TPHM, seeing the log likelihood, is more likely.
I got that. So, but if you can do this offline, if you find the best number in your opinion, why don't you send it to me? That would be all.
Hey, I'll do it.
Thank you.
This sounds like a good discussion for the breakout room too. Thank you again, Maddie. That was an outstanding talk and very informative. And we need to keep moving along. Well, here's our next speaker already, Christoph.
Start sharing the screen.
Go ahead and share your screen.
Here we go. Give me a minute to find a few.
Looks good.
Okay, my opening slide.
There you are. You're good.
Very good. So I'm going to give a similar talk to the first one given by Ataru. Although I won't be talking about population 3 stars, metal 3 stars, I'll talk about population 2 stars with about 1% solar metallicity. And I'm going to try to make the similar case and show you that it is actually quite natural for such stars, for such classical binaries, to produce merger with 85 plus 66 solar mass double black hole. Okay, so let me have a couple of general comments about a classical periinstability mass gap. So classically, like, you know, we all adopted in the community, the mass gap in terms of a black hole mass was somewhere about 45-50 to about 135. That's from old, I mean, not that old, but kind of 20-30-year-old Podsiadłowski papers and Stan Woosley papers. Okay, so, and that mass gap was always connected to explosive oxygen burning that disrupts the star or ejects outer parts of a star. However, even before the detection of GW 1905.21, we already did push that mass gap higher up. Okay, I admit that at least my paper, the number 3 on that thing, was based on the rumors that I kind of heard that LIGO did discover something heavier, but some of the works like Woosley 2017 or Limongi and Chaffee could not know that. So already before that event, stellar modelers were able to push that lower boundary of the upper mass gap to higher limits. So for population 3 stars, it was pushed by Stan Woosley to about 70, by Wing et al. To 85 in 2020. Population 2 stars that I will be talking about, 80 to 85. Again, stellar models, that's mostly mixing, convection, diffusion, winds. And for population 1 star, I've done a study with Raphael Hirschi with a Mesa code, and we have pushed that for population 1 stars, like in our stars, like in our galaxy, to 70 solar masses. Okay. Now, of course, after the detection, there was a lot of work being put on uncertainties that are associated with actually the actual position of a mass gap. And we already heard from Ataru and from others that, you know, if you take the very uncertain reaction rate for burning of carbon to oxygen, which is kind of, for me, it was such a surprise that such a basic reaction that produces 2 of the most common elements in the universe, it's so uncertain, but it could be uncertain by orders of magnitude. They call it a holy grail of reaction rates because it actually drives a lot of things in the universe, but it's highly uncertain. So when you throw uncertainties in that reaction rates, then you can push for population 3 and population 2 stars, the lower limit of the upper mass gap to 90 solar masses. And if you put on top of that some mixing and convection and dredge up uncertainties in stellar evolution, and that are connected to rotation and stellar winds and how you treat various issues, you can actually totally close the mass gap. You won't have a mass gap whatsoever. There will be continuous black hole mass distribution to whatever masses the stars can reach. And we don't know that. There's no first principle upper limit on the upper mass of a star. We simply don't know that. Okay? So I'm going to take those uncertainties. Maybe I will show the next plot. Okay, here I'm just showing that white region plus possibly a green region shows how the mass gap changes with the reaction rate that is marked on a horizontal axis. And you see that you can start as low as 50, 40 solar masses on the left-hand side and go to about 100, 20, and you can move the mass gap to about from 90 or 100 solar masses to about 180. And then, like I told you, if you add on top of that evolutionary uncertainties from mixing, you can close the mass gap altogether, okay? So taking this into account, I have just built the model that reflects that, and I allowed for stars to produce black holes up to 90 solar masses. What type of stars that would do that for me? So that plot demonstrates that on the horizontal axis, I'm showing initial zero-main sequence mass, and on the vertical axis, I'm showing a final helium core mass, which could be taken as a proxy for a black hole mass. So different color lines show different metallicities. So let's say for green line, black holes from to about 15, 20 solar masses, as expected in our galaxy, high metallicity, a lot of stellar winds, you remove most of the mass of a star before it collapses to a black hole. However, when you get to about 1% solar or even something below, this is that magenta line, you can produce black holes up to 90 solar masses, and the line stops, actually doesn't go all the way to initial masses of about 200, because this is where I start disrupting stars by perinstability supernovae. But in principle, I can form such stars. So I can do that. This is a single star evolution that I put in my binary model. So now, of course, I will have a very natural question. Okay, I can produce 90 solar mass black holes, or 60, whatever you ask me, up to 90. How natural it is actually to form pairs with 2 black holes being in that classical mass gap. How often do they form? Will they fit LIGO rates? Would I require some exotic formation channel? And can I produce low effective spin as measured by LIGO. That was my question to a previous speaker about effective spin for that system. But anyway, LIGO gives a LIGO effective spin measurement is consistent with that spin being 0. So it's not very big. So I've done such an exercise. It's a very simple exercise for me because I have all the machinery. And on the left-hand side, you can see the plot of a typical binary that produces such double black hole merger, like a GW 190521, in a standard binary evolution. I pretty much start with 2 stars. The blue star is a primary, about 200 solar masses. The yellowy star is a secondary, 150 solar masses. And I follow a regular double black hole formation channel that I have been forming double black holes with for like last 10, 15 years. So first I have a Rorschach overflow from primary to secondary. I lose most of the hydrogen envelope out of that star. I'm left with a compact core of about 85 solar masses. And that compact core will very quickly collapse its entirety, maybe a bit of a mass loss with neutrinos, but I will for about 85 solar mass black hole, direct core collapse. Okay, secondary star is on main sequence. When the black hole forms, then it expands after beyond main sequence, and then besides mass ratio is more than 2, that donor star, which starts common envelope, is much more massive. It's a dynamical mass transfer. It's a common envelope. It doesn't have to be that way, but that's a classical scenario. And I lose entire hydrogen envelope from the secondary star. I form about 65 solar mass helium core on a tight orbit around the black hole. Okay. That may be a subject to tides, so I may spin up that Wolf-Rayet star that will increase effective spin. I will give you the range for that in a second, but that Wolf-Rayet star will collapse very quickly to another black hole. And in about 3.5 million years, I have formed 2 black holes. One is 85 solar masses. That's that black hole on the left-hand side, and another one is about 65 solar masses. And the orbit is pretty small. It's only 12 solar radii. Such a system will merge in another 4 million years. So it took just 7, 8 million years of evolution from a very beginning, from zero main sequence to the final mergers of those 2 massive black holes in the most standard common envelope channel. Okay. So now let's compare. So we can do it. I can do it very easily if I take into account those uncertainties in a pre-instability mass gap. Now, how do we compare with other LIGO observables? So LIGO mass is 85 plus 65 here up on the top. My case, that example, it's 85 plus 65. That's really the same. Okay, LIGO merger rate density for such events, 90% credible limits, 0.02 to 0.4 per gigaparsec per year. My rate is kind of on the smallish side of that range, but it's within 90% credible limits, 0.04. Of course, I can tweak some parameters and bring it up, but I don't want that. That rate corresponds to my most standard assumptions in binary evolution. Then we go to effective spin parameters. So LIGO estimate goes from minus 0.3 to plus 0.35, with a kind of center peak being somewhere close to 0. I produce something between 0.1, 0.09 to 0.29, 0.3. It depends whether I include tidal interactions that black holes can put and spin up the Wolf-Rayet star. Then I have a lot of spin, and the secondary black hole would be a spinning black hole. That makes the effective spin of about 0.3. If I don't include tides, and we don't know how to really full include them, I mean, we do know how to include them for a given model, but we don't know which model is correct for tidal interactions. So I predict spin somewhere between 0.1 to 0.3, which is well within limits of LIGO 90% credible limits. What I cannot do easily is reproduce a precession, a high spins of those black holes being misaligned and precessing. So LIGO does provide the measurement of chi-p, which is a measure of precession in a double black hole merger of a more massive component, and that spin parameter is between 0.3 and 0.9. I get 0 because my black holes pretty much are non-spinning and are fully aligned with binary angular momentum. However, of course, I could try to give a big natal kick to one of the black holes to misalign that, but I think we have some evidence that those most massive black holes do form kind of symmetric collapse of entire thing to a black hole. You should not expect a large natal kick. So when I talked with people, I think that what was my question to Maya as well, that chi-p, that precession parameter, it's a very weak result and it depends very much on priors, and it's not very significant. For me, more significant thing here is that chi effective is small, because now we go to the discussion of whether this system comes from dynamical evolution when you have successive black hole mergers and you can form second, third generation mergers and could merge smaller black holes, even if a mass gap is in its classical regime, and you can form more massive black holes by successive mergers. But then black hole spins will be high, probably misaligned, and then you have a high precession. But effective spin would be also large. It would be very unlikely to have consecutive mergers that produce highly spinning misaligned black holes and have a very low effective spin. So I think that I rather bet that precession parameter is small and effective spin is also small. And that system comes from isolated binary evolution or just from those black holes come from single stars. So how much time do I have left?
You still have 9 minutes.
9 minutes, good. So I wanted to make, I will not hold you for too long. I want to leave some time for questions, but I wanted to throw at you something which is kind of only loosely connected to evolution of such massive system. If it was a binary that created GW 1905-21, I actually bothered to look for the most massive binary system that we know. I even have to admit that I didn't know it right up front. It is a system that was found in a Large Magellanic Cloud in S Dorado system, and it consists of two stars, 145 solar masses plus 131 solar masses. Both stars are still hydrogen burning, so they're relatively early in the evolution. Not even first million years of the evolution since the Riemann sequence. They're on a quite wide orbit. About 760 solar radii, so about 4 astronomical units. System is very eccentric, 0.7. So those stars are not really interacting very well within their Roche lobes. Metallicity is like LMC, it's about 0.006. So it's subsolar, okay? So now I ask myself a question, what would such a system force something similar to GW 1905-21? Or would it form even at all double black hole merger of any sort? So what I've done, I use various tools because we all know we have high uncertainties, not only in pairing stability, we have high uncertainties in rotation treatment, convection treatment, overshooting treatment, all sorts of things. So I took some simulation done with my code, which is Star Trek, that's the table on the left-hand side, with another population synthesis code that Ilya Mandel group has performed, and that those simulations were done by Dobatry, that's Compass code. Then I've done some simulation with Mesa, and here Jakub Klęcki and Amadeo Romogoldo helped with those simulations. Then I have Alexander Olejak doing Pawłowski model, which is a Natasha Ivanova models. Then I even evolved those stars as quasi-single evolution. So I have used a bunch of various tools to evolve that binary, which is with a very known configuration. We know masses, period, eccentricity, metallicity. We even kind of know the rotation of those stars because we have a very good spectroscopy. On a last column, you see the fate that I predict for that system. So in terms of a star track, when I use the most optimistic model for stars to survive interactions, I can form closed double black holes, not as quite massive as for GW 1905-21, but kind of, halfway mass. But I do form double black hole mergers. I go to another population synthesis code that is based on similar prescriptions. I form only white double black holes. I do simulation with Mesa. I never get to formation of a second black hole. I form one black hole, which gets sunk into the secondary star, and I form a Thorne-Zhitkov object, possibly a red nova or even a GRB, but it's a single object. If I use some Natasha Ivanova and Pawłowski prescriptions, I form I form white black hole binaries. If I treat those stars as single, because I give them a lot of rotation and a lot of mixing, they don't expand. It was the same story as Ataru was giving us. So those stars do not expand. They either form a wide black hole system, or they are disrupted by peri-instability supernova, depending where the peri-instability supernova actually happens. So I have all sorts of different outcomes. And why I'm making this point? I'm making this point because recently several papers appeared. They give a branching ratios between, let's say, binary evolution channel, globular cluster channel, and primordial black hole channel to interpret LIGO black holes. They say, let's say 50% come from that channel, 20% from that channel, and 30% from this channel. This is total gibberish. we have no idea, even within one channel, I'm only talking here about binaries, how a single system would evolve and what would it form. So it's good that people are developing tools to tell, those are Bayesian tools to tell between different channels, but by using very imperfect models, as you see, based on that table, that you cannot tell future evolution of one single system, okay? So the branching ratios between different channels that you get are based on imperfect models that are not covering even a small part of parameter space and are gibberish. So I think I would like to stop here. Thank you.
Thank you, Christoph. Very interesting talk. This paper is open for discussion. We have two hands up. Maya has a question. Oh no, that was applause.
Thank you.
But Maya does have a question, so.
Yeah,
Okay.
I actually do have a question. Yeah, so could you explain again how the low metallicity, you're able to produce black holes up to 90 solar masses? Is the idea that that you retain more of the envelope and that falls back?
No, it doesn't go with a mass. It is how you mix things. What's the opacity inside the star? So it pretty much all goes down to reaction rates, but that's not dependent on metallicity. But then the second factor that you need, those kind of non-zero metal stars, like population 2 stars, like about 1% solar, you need specific mixing to form cores that are large enough, but have temperature and densities in the center small enough as to avoid peri-instability region. So that's an interplay about many different various things. So let's say for solar metallicity, you can push it up to 70, but if we go above 70, we always get peri-instability. We always get temperature high enough for the star that it blows up. So, and then at that example that I was showing, I pretty much remove entire hydrogen envelope by companion from first star and from a second star. So I'm dealing only with helium cores. So you really deal with mixing within helium core, and you're trying to build such a temperature profile and density profile that you avoid, adiabatic index being, below 4/3.
Okay, Sam Mcdermott has a question.
Hi, yeah, very nice talk. I'm next, so I'll try to keep it quick. So Star Trek involves individual stars, or it's a population synthesis model, or
population synthesis model, but it goes binary after binary, or single star after single star. I can only do binaries and single stars.
I see. So it's not Mesa, like it's not evolving.
No, I'm using Mesa to calibrate my results though. That's it. But no, it's not like Mesa. It's a prescriptions.
I see. So the Mesa models that you use to build up that binary model, or that population model.
Yeah. So what I did when I got to let's say to a critical stage in a forming of double black holes in a population synthesis, whether it was COMPASS or Star Trek, I knew what the star looks like. And I took a Mesa to check whether whether I can eject common envelope. I checked the internal structure of the star with Mesa to actually calculate, binding energy. And I knew orbital energy from my simulations. So I could combine those two. And I call those Mesa models because I evolved the star to the same point. So I could really quantify all the things inside the star with Mesa, which is kind of a better tool than I have at hand.
Okay. Yeah, I may have some follow-up questions, but thanks.
Okay, Ataro Tanikawa has a question.
Okay, thank you. Thank you for very impressive talk, Chris. So I have a question about the maximum black hole mass. So I guess you can still lower the carbon alpha gamma reaction rate. So in that case, you can get more maximum black hole mass. So what is a possible maximum black hole mass?
Okay, so I could refer you to the paper by Guglielmo et al. That's a Michel 2020. That's a Michel Amapelli. When you combine uncertainties in reaction rates with the mixing rates, you close the gap totally. So there is no maximum mass of a black hole from stars. You go as high as you can go up with stars. And since we don't have a limit on a mass of a star, there is no fundamental limit on the mass of a star. There is no fundamental limit on the mass of a black hole of stellar origin. That's my statement for today.
Okay. Okay, thank you very much.
Okay, thank you again, Christoph.
Grant, before I need to apologize, please let me apologize to everyone. I'm giving a talk on another session, so I have to disconnect. I'm very sorry for that. I would love to be here to the end, but I need to. Sorry, guys. Thank you for all the questions.
Okay, thanks, Christoph. Don't everybody go to his session now. Okay, well, now we're going to shift into the new physics that is possible with the existence of black holes inside the mass gap. And our first talk on that is Sam Mcdermott. Sam, go ahead.
Okay, can you see my screen?
Yes.
Cool. Okay, great. Well, yeah, so thanks to Grant for the invitation. Thanks everybody for being here. I've learned a lot already, and I'm looking forward to more discussion. So this, the title of this talk is Find the Gap, just because there's so many papers and talks titled Mind the Gap. And so I'm going to be largely focusing on this most recent paper. All of this work has been done in very close collaboration with Trina Krohn and Jeremy Saxton. And we were joined by Eric Baxter on some papers, as well as an RU student, Maria Straight. So this paper here is the newest one. I said at AppJL because it just got accepted actually yesterday. And feel free to be in touch with me for further stuff like code sharing or anything like that. Okay, so the kind of one slide summary, because we're all on Zoom and it's hard to maintain focus for so long, is that we have demonstrated that we have the ability to change the black hole mass gap, the location of the most massive black hole, by using the new physics. And then we use the very beautiful LIGO Virgo gravitational wave transient catalog 2 that Maya discussed. We use that, we analyze that with this model of black hole formation and a variable mass gap to extract a value of the black hole mass gap. And depending on the assumptions of our data set, either with or without gravitational wave event 190521, we find a value, we extract a physical parameter from the data set, which is in more or less perfect agreement with the standard model prediction. So this is the summary. Here's some math that goes along with it, which I'll explain more as we go on. Okay, so we're all kind of experts here, I think, but just to kind of give the picture the way that I see it, the interesting question to ask is, how do we make very massive black holes? And so if you start off with a star of a certain mass, these are all metallicity dependent values, but for the choices that we ran here, if around 40-50 solar masses or so, if you increase the star mass, you increase the black hole mass. And so that just kind of is in one-to-one correspondence for a while. But at a certain range of star masses, as you turn up the star mass, you do not turn up the black hole mass anymore. So the black hole mass kind of flattens. That's due to pulsations. And then at a certain point, the black hole mass decreases. And then at a certain mass, in fact, there is no remnant at all. And so this maximum mass up here is the thing, the M mass BH and G, the black hole mass gap mass, which is of a lot of interest for this talk. So this is just kind of the cartoon. I mean, it's not really a cartoon because we actually calculated all these things, or more specifically, my collaborator Jeremy Saxton calculated all these things with Mesa. So just to give you some proof that we actually did some calculations and to give you some sense of what these calculations look like, we evolved stars from helium ignition to their final fate. We evolve, here we're showing 3 kind of characteristic masses, 40, 70, and 120. So this is kind of on the left edge of the figure, in the middle of that previous figure, and on the right edge of that previous figure. The 40 solar mass star just kind of evolves and collapses. There's not much to it. The 70 solar mass star has this complicated trajectory where it increases density and decreases its density and then increases again. And that's a pulsation. And so there's some remnant to that star, although it's a little bit less massive of a remnant than you might have expected because of that pulsation. Whereas this 120 solar mass star pulses very violently, explodes, unbinds, and there's no star left at the end, no remnant. And so this range here, and again, all these masses are metallicity dependent, but in the kind of 70 to 100 solar mass range, the star is experiencing pulsational pair instability supernova. And this higher range, 100 to 250 solar masses, it's experiencing the pair instability supernova. And so the first question to answer on that first slide is, can we change the black hole mass gap? And so the way that we do that is we posit the existence of new degrees of freedom or new kinds of physics in the core of the star that changes the way that the helium burning phase of the star acts, it shortens it. So it causes the star to consume fuel more quickly, so the helium burning phase is shorter. So the amount of oxygen that's available during pulsations is smaller, so explosions are less violent. And so mass loss is less pronounced, so there's a heavier black hole. This is kind of the step-by-step process. The thing that is happening during helium burning is the triple alpha process to produce carbon. A subdominant thing that's happening is carbon alpha capture, which produces oxygen. And oxygen really matters because that can burn explosively, which causes the pulsations. And so by shortening helium burning, by shortening this time, we are reducing this amount of oxygen. So here's some outputs from some Mesa simulations. On the x-axis, I have the new particle coupling strength. And so if I make that coupling very big, then the time to helium depletion is cut in half. And of course, I could turn it up even further if I wanted to turn down helium depletion even more. And that decreases the quantity of oxygen, so it increases the carbon to oxygen ratio, but what's happening is that there's less oxygen available during pulsations. So this x-axis, once again, is kind of a new particle coupling strength or strength of new physics. And so for a bunch of different models, and please feel free to check out these papers for more. In all of these models, as we increase the coupling, we see that this parameter MBHMG is increasing. So there's a positive slope to all of these lines, basically. So we did this with varying amounts of metallicity and so on. We did a fair number of cross-checks. And what we always found is that the larger coupling to new physics leads to larger black holes. There are standard model uncertainties on this. And that's due to both uncertain stellar physics, actual prescriptions deep inside of the star. There's uncertainties about what happens to the large massive envelopes of these stars, what exactly is happening with various plasma effects. There's observational uncertainties. So there's a lot, or possible redshift evolution also. Other things that can happen that can change these things. So yeah, in case this talk is being recorded and anybody's watching it later, also please check out all these other talks from this session. And of course, there can also be rare things that happen that change this mass. That change the mass of a black hole that you get to see. But the thing that I think is important, and the thing that I want to emphasize here, and which is going to kind of define the next part of the talk, is that if you think the universe is described only by standard model physics or by standard model plus beyond the standard model physics, those have very different predictions for the distribution of black holes, for the location of the black hole mass gap and the distribution of black holes up to that mass gap. So if you have standard model physics only, then the black hole mass gap is at the value predicted by the standard model in the calculation, unless there's major differences with what's going on inside of Mesa or nuclear rates or something. So you have some continuous distribution of black holes up to the black hole mass gap, plus some rare kind of pollutants above that. On the other hand, if there's beyond the standard model physics involved, and as I've shown, the black hole mass gap is not where the standard model predicts, and objects that are in what we think of as the mass gap can form from just normal isolated evolution. Nothing rare, nothing unusual about those stars is required. So there'd be some continuous distribution of black hole masses up to some new higher value of the mass gap. And so, as I've already kind of shown at the beginning, that doesn't really seem to be the case, but there's maybe some potential evidence in our analyses. So I'll describe all that in more detail now. I should also say that I took this quote from Chris Bolchinski earlier. Maybe we just simply don't know that value. Maybe this is just too uncertain. But I'm just going to assume that what we're learning from Mesa is about typical stars and typical environments, and actually kind of characterizes the standard model expectation in an accurate way. Okay, so here's a nice graphical depiction of the gravitational wave transient catalog 2 that Maya referred to earlier. So this is nice. Doing science on this distribution requires turning it into a mass distribution. So here's that mass distribution just on a linear scale or a log scale. I've shown that that distribution with and without GW 190521 because it makes a difference. It's an outlier. You can see that it changes the shape of the tail in a pretty significant way. Other things that you might note just by eye in this catalog is this broad feature around 30 solar masses, and the fact that it seems to end around either 80 or 100 solar masses, depending on with or without gravitational wave event 190521. Okay, so this is the catalog that I'm going to be working with. So here's the way that we're going to parameterize what the probability of having a black hole event with given masses is. Excuse me. There will be some distribution of black holes formed from isolated stellar evolution. That's what 1G means. It means they're first generation, so they're just black holes that came from stars, plus some population of pollutants, some 2G second generation black holes modulated by this parameter lambda, which I'm just going to assume is less than 1. So just there's fewer pollutants than there are isolated stars. And now this dn dmbh can be written this way, where theta is just some nuisance parameter. Oh, sorry, theta vector here, where underlying physical parameters. This is bad notation. Theta here is nuisance parameters. But so the idea is just that using the chain rule, I can integrate over some stellar mass distribution, which I know either from stellar IMF theory or something, or some other expectation, divided by this derivative. And this function is the thing that we have gotten from Mesa. And so that function, and then we use Bayes' theorem, which is shown over here in XKCD form. So this distribution is the thing that I kind of flashed earlier. It looks like this. And the kind of qualitative point that I want to emphasize is that this very wide range of stellar masses here. So here for this metallicity, it's shown from kind of 55 to 85 solar masses, initial star mass, maps to a very narrow range of black hole masses from kind of 38 to 42 solar masses or something. So that wide range of stellar masses got compressed to a narrow range of black hole masses. And furthermore, if you're thinking now about this black hole mass as kind of the x-axis, if you ask what black hole masses are there, there's this big pile up right at the black hole mass gap, and then there's nothing above it. So there's a bunch of stars at the gap and then nothing above. So we parameterize that in this way. The exact functional form is perhaps not so illuminating. It is, this is basically something that in a limit gives you a delta function, and then we multiplied it by additional factors of A to kind of make sampling this distribution easier. But for all intents and purposes, it's a thing that approaches the delta function. So it tells you how peaky the distribution is. So that's the 1G black holes. The 2G black holes, we assume, come from multiple 1G black holes. So I integrate over two products of this distribution, constrained so that their total mass equals the mass that I'm interested in. This isn't particularly important. What's important is when we run the analysis, do we get a reasonable looking mass function? And so here are our results. And notice I'm saying V2 here, that we found a small bug which essentially only affected our results with GW190521 for our model and did not affect anything else. So this panel is unchanged from V1. This panel has changed a little bit. In any case, we find a mass function when we omit GW190521 with a visible peak that's kind of right at 50 solar masses. And then it drops off and there's some pollutants above that. When we include GW190521, very interestingly, there is one peak in our posterior that has a black hole mass gap value that is lower than in the case where we omit GW190521. So by adding in this massive event, we've kind of shifted the posterior to have the black hole mass gap a little bit lower and to have a higher pollutant population. We have a second posterior peak, so it's kind of bimodal. There's another peak where the black hole mass gap value increased. I can show this a little bit more succinctly here. So our results are shown in the kind of orange or salmon color. And so this is comparing various dimensionful parameters from the LIGO-Virgo collaboration analysis versus ours versus the standard model expectation. So the standard model expectation is right around 48 solar masses, and our results lie right on top of that within 1 sigma. So the with GW190521 has this main peak at kind of 42, 43 solar masses, and a secondary broader peak around 75 solar masses, 70 solar masses. Without GW190521, our peak is at kind of 55-ish, 54, but extends pretty broadly to the left. And so the thing that is very interesting, so we calculate the evidence, and ours is comparable to the LIGO-Virgo analysis, their best model, the evidence for that. It's actually a little bit higher now after we've fixed our bug in the case with GW190521. But the thing to really emphasize is not that our evidence is a little bit better, but that we are extracting a physical parameter, which actually means something, that you can extract from the standard model prediction. Whereas this peak over here that you can kind of see by eye, that we don't really have a good physical understanding of where that would come from. This maximum mass also don't really know where that should come from, but we do know what this thing means. So I'll just conclude. I think I'm running out of time. Yeah, mostly all credit is due to the LIGO-Virgo collaboration for these really lovely discoveries. And yeah, I just want to plug these physically motivated mass functions, which I think are really giving us an insight into what's going on with the black holes. And I think the future is very exciting. So thanks.
Thanks, Sam. Very interesting talk. this paper is open for discussion. Let's see, I don't see any hands up. Could you just say a minute about the beyond standard model physics that you put in there?
So
You didn't refer to that much, but it in the end it doesn't help much. Is that right? And were there?
Yeah, in this case, we can kind of make the mass gap value go up to around 70-ish solar masses. And yeah, I mean, we don't get it to change by, 85 solar masses is still pretty large compared to the changes that we found. That's right.
Okay, there's a question from Maya.
Yeah, I guess one thing that I think is really interesting about this is that if you go back to the plot where you showed, like, yeah, this one. Yeah. So it seems like the maximum mass, so it's the orangish posteriors here, right? And it's like pretty below 70 solar masses. So some of like the previous talks with the physical uncertainties that would make it go past 70, like up to 90 solar masses. Like in your model, you're saying that that's not really like there might be black holes above there, but that's not the pair instability feature. Is that right?
Yeah, so when we include GW19-521, the main peak in the posterior has MBHMG around 40, but then the pollutant that value, this lambda, is relatively high. So we see a nice anti-correlation between MBHMG and lambda. And so it's really attributing GW19-521 and a lot of the other massive ones to the secondary population. So it's pretty cool, yeah.
Okay, well, thank you again, Sam, for a great talk. And next we'll move on to Michael Fabiano, who's going to tell us about the deep interior of the pair instability supernovae and the relativistic plasma screening. Go ahead, Mike. We can
Okay, so you should be able to see my screen now. I'd like to thank Sam for giving me a good title for this talk. So these are my collaborators here. We have a couple students indicated in red here as well, and I also want to make sure that I thank NASA and the Fulbright for providing a significant amount of funding for this work. So this is the outline of my talk. I'm gonna, in the interest of time, skip a lot of the stuff that, skip a lot of the math that we did, as well as some of the rudiments of plasma screening, but would refer you to some of these papers here. Kind of an interesting history here. We started this project 4 years ago, and then forgot about it for a couple of years, and then about last year we started thinking about a couple sites where this might be really interesting. And so in the past year we got 3 papers published with a couple submitted right now. In addition to black hole masses, I'm going to talk a little bit about how relativistic effects might affect pulse morphology, as well as some of the nucleosynthesis, which may be interesting to the observational astronomers. Probably will not get into 0.5 at all, which has application for other sites, but it's worth mentioning because it's kind of interesting. So this is just a cartoon of really what we've been working on for the past several years here. If I think of a nucleus at some origin at a coordinate, and I define the coordinate to be that nucleus, of course, you've got the Coulomb potential, and you can determine the thermonuclear rates by examining the penetrability through that potential. But of course, the background charges will change that potential, and if you shift the potential slightly, you can get a fairly significant shift in the thermonuclear reaction rates, because a lot of nuclear astrophysics lives down at the tail of the potential. And you can linearize the Poisson-Boltzmann equation to determine the shift in the potential, and at least for weak screening, and that's where most of this talk is going to concentrate, you get a Yukawa type potential, which is characterized by this characteristic length scale, often referred to as the Debye length. Depending on the screening model you use, it could be the Thomas Fermi length as well. The thing you want to keep in mind is when you linearize that, your Debye length is going to be that first derivative of the charge density. Worth keeping in mind that the enhancement to screening doesn't care what the sign of the charge is, and the reason is because, again, if I have a nucleus at 0 coordinate here, the charge distribution will change about that nucleus. It's Coulomb's law, right? The charge distribution will change such that you're always going to have an enhancement to that Coulomb potential. Which means if you add positrons to your plasma, and for hot plasmas you most certainly do, those positrons are going to create an enhancement to the screening as well. So just a little bit of background here, just some very brief background. A lot of the commonly used astrophysics codes, when it comes to weak screening, will generally assume a Boltzmann distribution for the electron density. And this is just the electron density that I'm worried about right now. We'll talk about the ion charge density a little later on, which again is a direct result of the Poisson-Boltzmann equation linearized to first order. However, for high temperature, you really do have to make sure you include the effects of the positrons. And so use a Fermi direct distribution. You can play some games to linearize this to make it more tractable for computational purposes. But you really want to make sure you include this as well. The chemical potential becomes very important, especially near the Fermi surface. Especially at high density. If you include magnetic fields, which aren't necessarily relevant to PPISN or PISN, your electron charge distribution changes, and this can actually have dramatic effects. Note also that this can have dramatic effects for the weak interactions as well. And we've explored a couple sites, but I mention it here just for completeness, just to let you know that this is something we've also considered as well. The electron energy distribution arranges itself in Landau levels. And for high enough magnetic fields, you can get significant changes not only in the thermonuclear rates, but also in the weak interaction rates, because it changes the Fermi distribution and the Pauli blocking factors. So how does this apply to pair instability or pulsational pair instability supernova? Let's see, I seem to be skipping a slide here. Nope, no, I'm not, I'm good. What's shown here on the left side is a plot as a function of temperature and electron density of the ratio of the Coulomb screening, the Debye length for what we call classical screening, the commonly used Boltzmann distribution, over relativistic screening. Keep in mind, larger lambda means less enhanced screening, smaller lambda means more enhanced screening, which means when this ratio gets bigger, relativistic effects become more important. And so you can see, of course, as your temperature increases, this ratio gets bigger. As your density decreases, this ratio gets bigger, and that's an effect of the electron chemical potentials. Again, I'm just thinking about the electrons right now. The ions are going to be a different story. So what's important here is really where do pulsational pair instability supernova live on this figure. On the right-hand side, it kind of gives you an idea of how this works, and what's shown here is a Mesa simulation. I use the simulation adapted from Pablo Marchand a couple years ago already, in which I'm plotting the this ratio, the ratio of the Debye screening lengths as a function of time and mass element. And so on the left-hand side, it's this figure projected onto just the time axis. You can look at the central temperature as a function of time before collapse. So time goes to the left here, and it's logarithmic, so you get the details of the pulsation here. And of course, you can see the pulsation, and you can see the unstable regions here. And depending on how you count pulses, you can get on the order of 10 pulses or so here. This is for a 70 solar mass helium core. So we start the evolution at the helium core there. On the right-hand side, it's the same thing. I'm only showing for temperatures above 150 keV. So it's not that there's nothing going on in here. I'm only showing the hot temperatures where the relativistic screening is going to be important. And you can see that the screening lengths change by as much as 30% or so. That could have a fairly significant effect, because the change in the thermonuclear reaction rates goes as the exponent of 1 over the screening length. So you've got an exponential term in there. And so you see that we're really only focused on the central, say, 20 solar masses of the star here, because that's where things are very hot. So as this evolves in time, you can see this first pulse here, and then you can see a whole bunch of second pulses here, and then some subsequent pulses there, and then eventually you're going to have the ultimate collapse here. I want to show you a couple figures about how this how relativistic screening affects the pulse morphology, just because it's interesting. And so this is, again, some results of Mesa Simulations, showing the central temperature as a function of time. Just for the first pulse, I'll show subsequent pulses later on. But we have light mass progenitors on the left-hand side. So this might be at the boundary of direct collapse and pulsational pair instability. And then we have heavy masses. So this is at the other boundary. This is at the PPIS and PISN boundary. So you have about 44 and 44.5 solar masses. And then in the middle, you have about 70 and 76 solar masses here. For the intermediate ones, you can see it doesn't change a whole lot, because things don't get really hot until the pulse. And so up until the pulse, the relativistic effects don't become too important. And there are some vagaries of the model that we did have to worry about here. Relativistic effects don't become important until about a temperature of 150 keV. That was imposed because of some numerical limitations, and we are exploring that. For the light ones, you can see that these what Stan Wolfsley, if I remember correctly, calls weak pulses, seem to occur for a longer period before the ultimate collapse of the star. You effectively get a little more heating, a little more enhanced burning in that region. For the heavy region, of course, you get the stabilities. What's particularly interesting is this 89.02 solar masses, which is where the relativistic model undergoes a collapse, whereas the relativistic model undergoes collapse, whereas the default model, which is in green here, continues on. So there's some really interesting effects there. What you're doing is you're shifting the boundary between pair instability supernova and the pulsational supernova. I'll tell you right now, that boundary doesn't shift by a whole lot. And I really appreciate Sam's comment. Refer you to slide 16 on Sam's talk, where he talked about the uncertainties in these models. And then the previous talk where we went over uncertainties. And that's going to become a serious consideration here. For the last pulse here, what I'm showing here are the subsequent pulses. Just think of zooming in on the subsequent pulses. And I just set time equals 0 to be the final collapse of the star. Although relativistic screening changes the collapse time, it changes the time from first pulse to last pulse, but I just set the final collapse to be at time 0 so that we can compare the default screening in green to relativistic screening shown here in red. This is a 52 solar mass, 52 mass helium core, 58 solar mass helium core, 64 and 70 solar mass helium core. And you can see, of course, there's some changes because of the burning changes. The burning changes in the core, you're going to change the pulse characteristics. What we're particularly interested in is how much time the star spends, how much time the entire star or the core of the star spends at high temperatures here. And you can see these axes are in days here. Okay, so it's not a lot of time, which actually ultimately comes and hurts us. But you can see there are some cases where you have this enhanced heating, enhanced screening, that can ultimately increase the reaction rates. And there's been some talk about the carbon-12 alpha reaction rate, and that was the one we're worried about. So time is fleeting here. So in the interest of time, I'll just show you the punchline, and not all results are particularly titillating. And this one was, unfortunately for us, a little disappointing. These are the black hole masses. You've seen this curve already in various forms. The black hole masses as a function of the helium core progenitor mass. And the black hole masses can change by, in some cases, about 1 solar mass or so, but you have to be careful that overall change is not likely greater than the uncertainties, any uncertainty of the model. So we do have to be careful. We have to explore that. Note that we didn't do a full parameter exploration on this. There's a paper by Farmer et al., which I think was the figure that Sam showed previously, which talks about those uncertainties. You can see here that the boundary between the pulsational instability and the pair instability supernova changes a little bit here, not by a lot. Maybe there's something else we can explore, but it doesn't change a lot. And then on the right-hand side, we have the change in the relative change in mass as a function of progenitor mass, and it's really only, at most 4 or 5% at the highest mass progenitors. So not very significant, fairly disappointing there. Just by way of advertisement, we did go on and look at some of the nucleosynthesis and the ejecta. So what this is a plot, again, as a function of the initial progenitor of the mass of the ejecta for, here we have carbon-12 on the left side, oxygen-16 on the bottom left. I'm sorry I didn't put labels on these. Where the green line is the default screening model and the red line is the relativistic screening model. Of course, most of that ejecta comes from the winds at lower mass, because you get this dredge up here, and you can see there's these black dots indicate the relative change in the amount of ejecta. You can get changes on the order of, say, 10% or so for the carbon, and 40% or so for the oxygen. And we talked to some of our astronomer friends about this, and they said, well, 10% it might be kind of iffy depending on what you're talking about. They didn't say it was impossible to observe, but certainly was, if you can do more, it's better. And of course, for the oxygen, you see a little more. Of course, when you get to the high mass, when you're in that PISN region, everything is ejected, and you expect little change because you're basically swamping everything with what's in the core. However, that could possibly change these heavy nuclei. Here we got iron 56 and nickel 56. And I would note that this is subject to the limitations of the reaction network we use. So we want to use a more robust reaction network, of course. But the difference in ejecta, of course, it doesn't seem to follow a trend, and it tends to reflect the instability of the model here. And so rapidly running out of time. So let me just show you the Kippenhahn diagrams for a 58 solar mass core, where these surfaces are defined where the mass fraction drops below 1%. You got the helium zone, the carbon zone, the carbon-oxygen boundary is shown here in red, and then there's some convective regions, certainly associated with the pulsation, and you get some dredge up here, but because of the changes in the heating and the reaction, you get changes in this boundary, and you can see for the default screening on the left side, there's some boundary change. You can follow this boundary, sort of this oscillation here. On the right side, you can see a little bit of a difference here, and in fact, you can see that the carbon-oxygen boundary actually shifts a little bit. And it has to do with where the pulsation stops, and where the boundary has to be when it stops. It's almost like you have this oscillation, and the boundary just stops. We did the same thing for various masses here, and just to compare, here's the Kippenhahn diagram without the convective region shown for comparing these two, where the dashed lines are the relativistic screening model, and the solid line is the default screening model. So when you get this dredge up, that could manifest itself in some observational effects. If we get a confirmed observation, could possibly manifest itself in galactic chemical evolution effects as well. Okay, my time is up, so I'm just going to put my conclusions up here. We're starting to think about this lower mass gap, which could be affected by things like protoneutron star cooling, high fields in the neutron star, a very different physics down there. Okay, I'm done. Thank you very much for your time.
Okay, thank you, Mike, for a very interesting talk. I guess the secrets of the deep interior of these massive stars. This paper is open for discussion. Sam has a question.
Yeah, I like the old physics and the mass gap. Yeah, so I mean, I think you're kind of like getting at it or hinting at it in this conclusion slide, but is the mass gap, like, it seems like the mass gap is not the place where this effect is highlighted. Like, is there what's your intuition for what this effect would be most visible in?
Yeah, you really hit it there. So when we're dealing with just massive stars, I mean, we're kind of hoping, right? You're always hoping that what you're doing is going to have some kind of effect, and we were sort of vaguely disappointed when we didn't see a huge change in the mass gap, especially in this 70 or 76 solar mass progenitor. The change lies more in the nucleosynthesis there, particularly when you're dealing with a dredge up there. I mean, you're seeing effects of 10 or more % for some of these lighter nuclei. And of course, you got to make sure you do the nuclear reaction network right. And you got to make sure you probe the whole parameter space. And of course, I've got this advertisement here at the bottom. We've explored a lot of other sites, including collapsar nucleosynthesis. Biggest effect we've seen was in collapsar nucleosynthesis, because you're compounding the effects of the magnetic field effects on the screening, as well as the effects of the magnetic field on the weak interaction rates. So our PPISN, PISN, is that where it's at as far as relativistic screening goes? There's a few other things we can look at. This lower mass gap, as you know, is a completely different zoo in terms of the physics, and so we might investigate there, because now you're dealing with things like, you might get an accreting neutron star. I read a paper just 2 days ago about accreting magnetars as a possible site as well. So we may think about it a little more, but we'll probably leave it to the cooler stuff. We'll leave it to your paper there.
Cool.
Okay. So I don't see any other hands up, and we're running late in the session. So let's have the last talk by Joshua Ziegler, who's going to tell us about adding non-nuclear energy. Go ahead and share your screen, Josh.
Mm-hmm.
We can see it.
Okay. Thanks. All right, so I wanted to start by thanking everybody for sticking around for this, and for Grant and the organizers for inviting me to give this talk about some work that I've done with Katie Fries, and specifically looking at the sort of stellar modeling of what happens when you introduce non-nuclear energy to stars and how that affects the mass gap. So we've talked about the mass gap so far quite a few times. Here's just a bit of a rehash. For stars that in this mass range of about 140 to 240 solar masses, the stellar core gets hot enough and dense enough to start producing electrons and positrons, and that ultimately leads to a collapse of the star. And you expect there's no black hole masses in this mass range, 50 to 140 solar masses or thereabouts. And that comes into contact with the recent GW 1905-21 results that we've talked about quite a bit. Just in general, there are different ways that you can play around with this mass gap, but because the physics that is underlying this in terms of the electrons and positrons production and the oxygen burning leading to the parent stability supernova are all fairly well understood up to various nuclear reaction rates. There are fairly large uncertainties on, but the physics itself is relatively robust. And so the existence of the mass gap in most cases tends to still exist with some uncertainty on where exactly it falls. So the question that we're trying to address is essentially how much can we play with this? What does it take to actually avoid reaching that parent stability? And in particularly, we're looking at whether new physics could allow us to produce black holes in that gap. And so a lot of what I'm talking about sort of dovetails with what Sam was talking about, except that the model that we're looking at is based on sort of continuous energy production throughout the star, throughout the stellar lifetime. And so hydrogen burning, helium burning, all of these different phases will each produce less of their respective results. So the core gets considerably smaller over the entire lifetime of the star. And sort of a motivation for this is the idea of dark matter annihilations providing extra energy. Essentially, if you have a dense enough amount of dark matter in the star, then for things like WIMPs or self-interacting dark matter, the annihilation cross-section can lead to annihilations, which then give you electrons and photons that can then thermalize with the star around it and provide the extra energy. That is just sort of one model that we have in mind, but in principle, what we have, the results that we find by doing this stellar modeling can be sort of generalized to any model that introduces an extra energy source. So what exactly are we doing? essentially what we're just looking at Mesa stellar modeling, where instead of just using the generic stellar evolution equations, the stellar structure equations, we introduce a non-nuclear energy term. And that term can have essentially any functional form, depending on your different model, as long as it is it goes to zero at the edges of the star. So the simplest case that we found that worked was using just a constant energy production rate per mass of the star, or for the epsilon non-nuclear. And so that's what we worked with in this star, in this modeling. We focused on 180 solar mass stars, which will, in the standard picture, will fall into the parent stability gap. But in this case, just sort of to give a preview, we find that they don't. So again, using our, so while we are using this epsilon non-nuclear being a constant, it isn't exactly what you would expect from dark matter annihilations, but the results should be similar on the broadest, in the broadest terms. Okay, so talking about the results now, this is just sort of the default modeling that you would get from without any sort of standard, without any extra energy. You have, in general, the temperature and density of the star, the central core of the star, increases from the beginning of the star to the end. And as time evolves, you move to higher temperatures and density. For stars that undergo parent stability, you reach a maximum temperature and density before rapidly decreasing. And that's the explosion that comes from the parent stability. And so in our modeling, we use this condition that the entire mass of the star is moving outward faster than the escape velocity as our condition for defining the parent stability supernova. And so for the 180 solar masses, that leads to a parent stability supernova directly with just the standard evolution. If we add in extra energy, and in particular, the case that we found that gave the most interesting results was adding in this value of 2.2 times 10 to the 4 ergs per second per gram of extra energy, which corresponded to 60% of the energy needed to support the star during its main sequence. If you add in this extra energy, rather than reaching a maximum temperature and density, the star evolves to continuously increase the temperature and density until you reach a core collapse supernova, which can give a black hole remnant. And sort of the main result of that is that this particular model with this amount of energy, this 180 solar mass star with 2.2 times 10 to the 4 ergs per second per gram of extra energy gives rise to a precursor. We didn't follow the evolution through the supernova, but to the pre-core collapse supernova precursor of 119 solar masses, which is very likely to lead to a black hole in the mass gap. So that's sort of one of the main results that we found. The other interesting result is that you can also get some different potentially observable effects because of a period of dredge up that happens during the carbon burning phase, so sometime around 95% of the way through the lifetime of the star. You have this chemical mixing that happens, which drags carbon and oxygen out of the core into the envelope. And the hydrogen and helium down into the core, which causes some changes to the evolutionary track, which you can see as this sort of zigzag pattern in the evolutionary track. And what's interesting about this is that it has a lot of different effects. First of all, for the core mass, the core mass itself goes down relatively fairly large amount, from about 40 solar masses to about 20 solar masses, as a result of this mixing, this dredge up. And after this dredge up happens, you start to see the effects of having metallicity. Even though we started with a 0 metallicity star, you have now got a atmosphere with non-zero metallicity, so you can start seeing much higher mass loss rates due to the stellar wind, and you can potentially see some observable effects in the surface spectra. If you were to look at these stars late in their lifetime, there might be spectral signatures. But maybe the most interesting result for the sort of methodological result is that in these particular stars, the envelope itself is important, and understanding how that envelope interacts with the core is important in even these very high mass stars. Okay, so conclusions. Essentially, by adding in this extra mass, which has a fairly simple form, we can evolve stars into the parent stability gap. And dark matter may provide some model for this, though it is relatively uncertain, I guess, as to how to actually generate the densities needed. Okay, well, thank you for all for listening.
Well, thanks, Joshua, for a very nice talk and sticking to the allowed time. And this paper is open for discussion. Sam, of course.
Yeah, hey Josh. So so maybe I misunderstood. I thought from the paper, I thought that you evolved like all the way through explosion, through pulsations. Is that?
Yeah.
Oh,
right. Sorry, we didn't evolve through the core collapse supernova. We evolved through pulsations when we had those in like pulsational parent stability, but we did not evolve all the way through the core collapse supernova that you get normally, direct collapse supernova.
Yeah, so you found, I mean, you did the same thing, you found stuff that was gravitationally bound.
Yeah, exactly.
And then my other question was, so is this code like uploaded to the Mesa list or whatever? Is that, do you plan on doing that?
We can, yeah. It's more or less just the pulsational parent stability example code with some modifications, but yeah, we can definitely upload at some point.
Cool. Okay. Yeah. Maybe we'll be in the chapter. Cool. Thanks.
Any further discussion?
Yes, I have a question.
Yes.
So thanks for the talk. So this is interesting. So I would like to know about the energy deposition profile. So how do you determine the profile inside the star when you, because this is a density?
So it's a density in that it's an energy per gram, and just based on the I guess, what do you mean by the energy in the star?
So where do you put the energy?
Okay, so all throughout the star, anywhere that there's mass, we just add in this, the extra energy, the energy per density, energy per gram of stellar material. So wherever there's stellar material, there is this extra energy added, proportional to that amount of stellar material. So there's more energy deposited in this the core, but it extends all the way through the envelope as well.
I see. Sorry, maybe I have a short follow-up question. So does it how much dark matter local density does this correspond to? And if it is applied to the whole star, how would it affect if we consider a lower mass star? Will it be very large effect, which is might be unphysical?
So it depends on how much mass or how much energy gets added, of course. This is fairly hard. It requires a fairly large amount of energy to be added for there to be any noticeable effect. We had to add 60% of the energy from this non-nuclear source in order to get any really noticeable results. So in terms of just adding a little bit of energy, it really won't give you much new result, a particularly interesting result. As far as how much the local density is, I can't remember offhand what the number is, but it's very large, larger. It's considerably larger than you would expect in most astrophysical situations. Even in the cores of galaxies, you're probably not going to get the density needed to see this. But in terms,
yeah, go ahead. But just to follow on Katie Freese's dark star idea, and the preface to that was that you had to form these stars when the dark matter density was much higher than it is now. So these were stars formed very early on and are mainly very massive, and that's when you get the effect.
And added to that, you also have, in order to get the dark stars that Katie worked on, you also have to have adiabatic contraction effects, which further increase the dark matter density. So it's very high densities of dark matter. In principle, these would only, using dark matter as the energy source, you would only really see this in early type stars.
Okay, well, I don't see any further discussion, so we should thank all the speakers and the attendees for very interesting talks and very lively discussion. We're not going to get kicked off until 5 more minutes, so anyone that wants to continue discussion is welcome to stay. But other than that, we are finished, and enjoy the rest of the workshop, the conference.
Thanks everybody. But yeah, nice, cool talks.
It's a great session. Okay, I guess I should stop the recording.